Okay, hello everyone. Thank you so much for joining me today. This is the last of five review sessions for a Math 111, Calculus 1. Today it's going to be on L'Hopital's rule, linear approximation, and curve sketching. And we're just kind of going to go through all of the processes to hopefully get you to excel on your exam. I hope your studies are going well. Um, my name is Mitchell. I'm one of the Math 111 instructors. Okay, let's get started. Okay, so the first thing that I really want to hit home with about L'Hopital's is this question: What are which of the following are indeterminate forms? So there are actually more indeterminate forms than the four that I have listed here, but we didn't talk about them in class, and they won't show up on the final exam, so I don't want to have them in here. And I think the heart of this question gets at what? Oh, that is kind of thin. So let's make it thicker. So the question is, what is an indeterminate form? So we never really talked about it in class, right? We kind of, hinted at it, right? But to be explicit, it's something that like two different functions or properties that will go to the same thing but are fundamentally different, right? So for example, I'm gonna let you in on a little secret. This infinity minus infinity is an indeterminate form, and we know it's an indeterminate form because we can think about it as, right, the limit as x goes to infinity of x squared minus x, right? Obviously, in this case, we see that this is an infinity minus infinity limit, right? And the x squared term is obviously bigger, right? For any positive x value greater than 1, x squared is going to be greater than x. So x squared minus x is going to be positive, right? Um, so we know that in this case, right, if we were to factor them and everything, we would see that this goes to infinity, right? Because x squared is bigger than x, right? So obviously we're subtracting, a bigger infinity by this, so it's going to go into infinity. However, the roles could easily be reversed where we have x, the limit as x goes to infinity of x minus x squared, right? Where it's the exact same limit type because as I plug in infinity, I still get an infinity minus infinity, but this time it's the exact opposite, right? We see that x is always going to be less than x squared as long as x is bigger than 1. So this is actually going to converge to negative infinity. So we have two different limit types, right? Two different limits, excuse me, that are the same type, right? This is an infinity minus infinity limit. This is an infinity minus infinity limit, but they go to different values. So that's why we call them indeterminate. And there are plenty more examples just in this case, as well as all the other cases that we're going to talk about, where we can see that, the same setup is actually going to lead us to two different answers. So it's indeterminate, right? Just because it's infinity minus infinity, we can't tell which it's going to go to. Is it going to go to infinity? Is it going to go to negative infinity? Is it going to go to zero? It doesn't, for example, if we had something really boring, x, goes to infinity, x minus x. Again, it's infinity minus infinity, but here we can clearly see that, well, x minus x for any value is going to be zero. Therefore, this is going to go to zero, right? So there are many, many more examples that we can have here where they're all of the same form, infinity minus infinity, and they converge to three different things. So just because we have infinity minus infinity doesn't mean we actually know what is going on. Right. So that's why that is an indeterminate form. And for the rest of these, I think it's good to just kind of go through them one by one and see. It's really important that we understand what are indeterminate forms, and more importantly, what are indeterminate forms that we can use L'Hopital for, right? Okay. So as I said, infinity minus infinity is one. Let's start here, right? Zero to the infinity, right? So this, it might look like an indeterminate form, right? But actually it's not, right? So if we have like limit as x goes to infinity of like 1 over x to the x or something, right? This is getting closer to 0. This is getting really, really large. This is a 0 to the infinity limit. However, we could think of this as this is getting really, really small, very, very close to 0. And this is getting much larger, right? So we could approximate this as like something like 0.0001 to the 10,000. So because, I'm sorry, one extra zero. So because of the fact that this is very small and we're multiplying a small number by itself over and over and over again, it is actually going to go to 0. So this is not an indeterminate form. Okay, you probably also see the kind of canonical ones, the 0 over 0 and infinity over infinity. These are the ones that we talked about in class where we explicitly said those are indeterminate forms, right? And again, examples include things like just x, powers of x, right? So I could have x squared over x. I could have something like this, x squared over e to the 3x, right? This is an infinity over infinity, but it could just as easily be flipped upside down, and we'd get very different answers, but it's still an infinity over infinity limit. Okay, and I said there are four, and I've only checked one more. I know it's not this one. So 1 over 0, we could think of this as any fixed number, so let's say 1, or it could be 2, 3, 7.5, right? Over a really, really small positive number, right? So because we have any fixed number and we're dividing by something really, really small, that's equivalent to multiplying by something very, very big, right? So this is actually going to converge to infinity. So we can't forget that, right? When we're looking at indeterminate forms, we knew a 0 over or a 1 over 0 limit already went to infinity. So we can't forget that this is not an indeterminate form. And then we have 0 over infinity and infinity over 0. Again, we need to think about this, right? If I have a number very close to 0 and I divide by a number that's very, very big, something like, this, we see that, well, this is just going to be 0. We have 0 divided by a really big number, still 0. Okay, so that's not an indeterminate form. And lastly, this other one, this infinity over 0, is kind of a culmination of this argument, right? Where if we have a really big number and we're dividing by a very, very small number, that's almost the same as having a really big number times a really big number, which is infinity, right? So we know what these are. Just because a limit goes to infinity doesn't necessarily mean that it's an indeterminate form. Okay. So that means, last but not least, we have this 0 times infinity. And this is really important that we understand that 0 times infinity is also going to be indeterminate. And I'll show you a quick example, right? Over here, we have limit as, you know, maybe we have something like 1 over x times x as x goes to infinity, right? Obviously, this is going to converge to 1 because of the fact that x divided by this is just 1 for every value. So this equals 1. And again, this is a 0 because as x gets very big, 1 over a very big number. And then this is 1 over a very big number, which is going to be 0. And then this is a very big number. So this is, again, a 0 times infinity problem. But just by playing around with powers of x, I could get something like this, right? Where we have 1 over x squared times x. Again, this is as x gets big, 1 over a very big number goes to 0, and then we have a very large number, infinity, right? This obviously is going to equal the limit as x goes to infinity of 1 over x, which we already talked about over here, right? Um, or not that one, excuse me, but something where it would be like a 1 over infinity limit. Um, and so we know what that equals. That is going to go to 0. But again, we could just play around with these powers and do 1 over x times x squared, right? Obviously, this is again a 0 times infinity limit, but this time the behavior is much, much different, and this time it's going to go to infinity, right? So that is what an indeterminate form means, is I have forms of all the same kind, right? 0 times infinity, 0 times infinity, and 0 times infinity, and they converge to three different things, 0, 1, and infinity, right? So that is why they're called indeterminate forms, and that is how we identify them. So I think on the exam, you won't have to necessarily know all of them, but it's very important to know when you can and can't use L'Hopital's rule. And if we see something like this, for example, because it's not a 0 over 0 or infinity over infinity case, as we talked about in class, we do need to rewrite it so that it becomes a 0 over 0 and an or an infinity over infinity case. And we're gonna do that shortly. Okay. So I'm gonna clean up some of this work, right, and only show work for the ones that are um, indeterminate forms. So this is not an indeterminate form. Okay. And as well as the recording, these notes are going to be posted, right? So don't worry if I'm erasing something and you wanted to see it, because they're going to be posted. Okay. So now that we know kind of all of the indeterminate forms and when we can apply L'Hopital's to it, right, we're going to compute the following limit, right? So the limit as x goes to infinity of x cubed over e to the 3x. The first step with any L'Hopital's question is try to plug it in exactly, right? And see what happens. Maybe it's well behaved. I don't know. Right? So if we plug it in exactly, we see that a very large number cubed is going to be a very large number and going to infinity. And then as we know from exponential functions, e to x, as x gets very, very large, is going to be e to a very large number, which is infinity, right? So we've established that this, in its current form, is an infinity over infinity limit. So that means that we can use L'Hopital's to justify it. And in fact, we are going to need to write where we use L'Hopital's, right? So this limit, and I'm going to denote that as like LH over the equal sign, saying I've applied L'Hopital's here, right? And L'Hopital's rule says that if we have an infinity over infinity or a 0 over 0 limit case, we can take the derivative of both the top and the bottom independently, right? So we don't have to do the quotient rule here. We can take the derivative of the top and the derivative of the bottom and then check and see how it works, right? So that is the same as saying the limit as x goes to infinity of 3x squared, the derivative of x cubed, over, and then this one is going to be a chain rule situation, right? So we take the derivative with respect to the outer function times the derivative with respect to the inner function. So we get 3x squared over e to the 3x times 3. Okay, so now let's try to plug it in and see what's going on. Again, I'm seeing x squared, that's going to go to infinity, and then e to the 3x, we didn't get rid of that by the same argument as above, it's going to go to infinity, right? So we still have an issue because we have an infinity over infinity case, so that means that we have to do L'Hopital's again, right? So either I started here and I got here, or if I was just given something here, it's infinity over infinity. I have to do L'Hopital's to figure out. Okay, so then by L'Hopital's rule, we get the limit as x goes to infinity of 6x over, and then because again, this is a chain rule, this is going to be 9 e to the 3x. Okay. And then again, I'm looking at this, I'm plugging it in directly. This is going to go to infinity. This is also going to go to infinity. So I check again. This is a L'Hopital's question. So that means by L'Hopital's rule one more time, hopefully, I end up with the limit as x goes to infinity of 6 over, and then this is going to be 27 e to the 3x. Okay. Now I don't have an infinity over infinity limit. In fact, this for all x is going to stay 6. It's a constant. And then here, this is obviously going to get very, very large, and it's multiplied by a positive constant. So we see that this is going to be going to 6 over infinity. And as we just talked about, this equals then 0 because of the same argument we had up here, right? Um, any constant divided by a very, very small number is going to go to 0, right? And there's a fun way to kind of circumvent this. Obviously, on the exam, we would want you to do all of this work, right? But looking at this, we can look at growth rates, which we didn't really talk about in this class, but it's useful if you ever want to go into like computer science or something like that, where you see that x cubed, that is a polynomial, and e to the x, that is some sort of exponential function. And by looking at these graphs, we know that e to the x grows faster than x to the p. And I'm going to put p here for any polynomial. In this case, x equals 3, right? So we knew if we knew growth rates, we would know that e to the x grows faster than x to the p. So obviously, the bottom is going to grow faster than the top. And if that's the case, the bottom is going to get much, much bigger. So it's going to converge to 0. And we can justify that formally by looking at this work, right? We see that the derivative of polynomials are always going to go down a degree, whereas e to the x is going to stay itself times some constant factor up front. Here it's 3 and then 9 and then 27 and then it gets bigger, right? But it could also be like 1/3, 1/6, all of that. But doesn't matter because the e to the x power or e to the x part still stays the same. Okay. Awesome. And one thing I want to say is if there are any questions for the 12 people who are here, feel free to just unmute yourself. I'm not monitoring the chat. I'm just looking at my screen. So feel free to unmute yourself and stop me if you have any questions with the caveat again that this is being recorded. So if you don't feel comfortable, you could put it in the chat and I'll try to catch it between every question. Okay. So now we are going to continue with L'Hopital's rule. And in fact, we have a slightly different looking function. So consider the function r of x, which is x times ln of x plus 67 over x, right? Um, so which is the correct form of the limit as x goes to infinity, right? So obviously, as x goes to infinity here, right? We know it's going to be infinity times something, right? So unfortunately, I cannot get rid of any of the choices, right? It's infinity times something. And so I need to figure out what the limit as x goes to infinity of ln x plus 67 over x equals, right? So there are a few different ways that I could do this. One, I could realize that if we plug in x here, I get an infinity over infinity case. So that means I'm going to have to do um, L'Hopital's and see what comes out of it. Um, or we could rewrite this as the limit as x goes to infinity of ln 1 plus 67 over x, right? Because this is a sum on the top, I can take this x and give it to both terms. So I would have x over x plus 67 over x. Well, x over x is 1. And hopefully now this is more apparent what you have to do, right? Um, we would have to see that as x gets really, really big, the only where x shows up is here. And as x gets very big, no matter what the constant is, it's going to be equivalent to like a 1 over infinity, which goes to 0. So then this means this is equal to ln of 1 plus 0, right? But ln of 1 is one of those things that we absolutely need to know, and in fact, it equals 0. So that means after all of this computation, I was able to see that this is a 0 times infinity limit. Okay. Because as x gets very, very big, this gets very, very close to 1. ln of 1 is 0. Okay. So this means I cannot use L'Hopital's rule exactly, even though this is a indeterminate form that we've just talked about, right? So I'm going to have to figure out a way to rewrite this so that it becomes a 0 over 0 case or an infinity over infinity case. Both are valid. I'm going to try to do both. There's one that makes it really, really easy, and the other one is actually kind of hard, and I'm going to try to demonstrate both for you today to show you what I mean when I say if the math isn't becoming easier, then try the other way. Okay. So this is an infinity times 0 case. So I am going to look at rewriting it, the limit as x goes to infinity of x ln of x plus 67 over x, right? We could rewrite this as ln of x plus 67 over x over 1 over x, right? Because multiplying by a number is the same as dividing by its reciprocal. We know this, right? And now if we sorry, I want to be more clear here, so I'm going to move this over and write that they're the same in limits. Limit as x goes to infinity, right? Okay. So now, as x gets really, really large, this goes to 0, as we've already established. And this is now 1 over infinity, which is going to go to 0, right? So this is a 0 over 0 case. So this means that we can now use L'Hopital's because we can only use L'Hopital on 0 over 0 or infinity over infinity cases. Okay. It's very important that we remember that. And if we get like an infinity times a 0, a negative infinity times 0, something like that, we have to rewrite it. Okay. So now, by L'Hopital's rule, I will get that this equals the limit as x goes to infinity of the derivative of the top. Well, ln is one of those special derivatives that it is just going to be 1 over the argument inside, right? So this is going to become, in the derivative form, 1 over 1 plus 67 over x, right? Where I simplified x plus 67 over x as the same I did up here, right? But this is a chain rule, unfortunately, so we can't stop there, right? Now we need to take the derivative with respect to the inner function, which is 1 plus 67 over x. X is actually going to be, we could rewrite that as 1 plus 67x to the minus 1, and then that's exactly what we're going to need to do the power rule, where then we get minus 67x to the minus 2, right? And then here, 1 over x, we could rewrite that as, x to the minus 1 as well. And so then we again get the same sort of situation. By the power rule, we get 1, x to the minus 2. Okay, so now the math became really easy because I see that there's an x to the minus 2 here and an x to the minus 2 here, right? Okay, so that means I can get rid of them, and we get minus 67 over 1 plus 67 over x as our answer. Um, Excuse me, there's a minus sign here. So it's a plus 67. Okay. And now, as the limit gets really, really big, x gets big here, but it's in the denominator. So 67 over a very large number is actually going to be 0. So we have 67 over, and I'll write this here, right? This equals 67 over 1 plus 0. So we end up with 6, 7 as the answer. So I'll put a box around that because that's the answer here. Okay. Okay. Let's see the other way, right? So I'm going to write this in a different color just so we don't get confused. Um, but what I did here is I ended up where I took the x and I moved it to the bottom by multiplying by its reciprocal, right? So x became divided by 1 over x. What if I want to switch it the other way, right? Let's see what happens if I do the limit as x goes to infinity, and instead of moving the x down, I move the ln of x, ln of all that down. So I get x over 1 over ln of and I'm going to make my life easy. I'm going to do 1 plus 67 over x. Okay, so already this is looking kind of difficult. I don't necessarily want to do this, but we'll carry on nonetheless, right? So as x gets very, very big, okay, that's going to infinity. And as x gets very, very big, remember we said that this is going to go to 1, ln of 1 is 0, so we have divided by 1 over 0, which goes to infinity, right? So now in this case, we have an infinity over infinity case. Okay. Now we can use L'Hopital's and take the derivative of both the top and the bottom, the limit as x goes to infinity of 1 over, and so this is going to be tough, right? I'm going to do some work over here, right? This actually equals ln 1 plus 67 over x to the minus 1 in the denominator. So I'm going to have to do a chain rule, right? So if I do dx, right, this is going to equal minus 1 ln 1 plus 67 over x to the minus 2, right? But then I need to multiply by the derivative of the inside, right? The derivative of the inside is actually this entire function, right? So times dx ln 1 plus 67 over x, right? And I think we did this up here already, right? So we'll be good there. Um, and we see that this is going to equal minus 1 over ln 1 plus 67 over x squared. Put a bracket around there so we know it's squared. Um, and then the derivative of this is going to be 1 over 1 plus 67 over x times this minus 67x to the minus 2. Okay. So I'm not seeing really anything that can cancel here. And in fact, I think the calculus got worse, right? So as the limit as, x goes to infinity, right? So if we were to rewrite it, we would have 1 plus 67 over x ln 1 plus 67 over x squared, and then the top is now going to be minus 67x to the minus 2, right? This is still not looking good, right? Because as x gets very, very large, this is now 0. This is 1. Actually, I lied. It does simplify very nicely, right? This is 0 squared. This is 1. And then and then this would come down, and it would also be something times infinity. Actually, I lied. So this is 1 over infinity times 0, right? So it actually didn't make anything easier, right? And this whole thing looks a lot worse to differentiate than the starting point. So if I saw this on an exam, what I would do is I would stop, I would reflect, and I would say, I'm still getting a 0 over infinity, or we could view this as a 0 over uh 1 over this, right? We could rewrite it such that it becomes an infinity over infinity or a 0 over 0. That's never the case, right? That made our lives harder because we have the same problem and we're not finished, right? So I would personally go to the first method if I tried this way, right? There's no harm in trying this and seeing what happens, but what's shaking out is something that's really ugly. Okay. Are there any questions about this? Okay. Seeing none, let's continue forward. And so now you might look at this next, I don't know why it says integral there. It should say limit, right? But you might look at this and say, oh, well, it's not a limit to infinity, so we're golden, right? It's not going to be a L'Hopital situation. Unfortunately, you would be wrong, right? Another thing you might look at and say, oh, I could factor this. This is factorable, right? It's quadratic in x squared. Sure, but it looks really messy. And I don't know how to factor this necessarily, right? So you could try to factor it. Good luck. I had no luck with it, but maybe you're better than me. But if we plug in this t goes to 1, right, we get this is going to be 5 times 1 minus 4 times 1 minus 1 over 10 minus 1 minus 9 times 1, right? So this becomes 5 minus 4 minus 1, 0. This becomes 10 minus 1 minus 9, 0, right? So we do actually end up with a 0 over 0 situation. So we're going to have to do L'Hopital's here, right? So what we're going to do is the limit as t goes to 1 of 5t to the fourth minus 4t squared minus 1 all over 10 minus t minus 9t cubed by L'Hopital, right? LH. What we have is we can take the derivative of both the top and the bottom independently. So we end up with 20t cubed minus 8t, and then the 1 goes away, and then we are dividing by the 10 goes away. We have minus 1 minus 27t, right? Okay. One thing I forgot to put, and you would lose points for on an exam, so good thing I'm catching myself, is they're only equal in the limit as t goes to infinity, right? They're completely different functions. They're only equal in this limit case, right? So when we do L'Hopital, we have to be consistent and keep that limit as t goes to 1, not t goes to infinity. Okay. Great.
Sorry to interrupt, but shouldn't there be like a t squared on the denominator?
Oh, yes. Thank you. It's not going to matter because right now we're going to plug in 1 and 1 times 1 is still 1, but yes, you are absolutely correct. To be the 3 comes down, so that's where we get the 27 and then t and then 3 minus 1 is 2. Okay. So now we're going to plug in t going to 1, we get 20 times 1, right? T cubed is just 1 minus 8 times 1 over minus 1 minus 27. Again, t squared is going to be 1. So this simplifies to 12 over minus 28, which there's a common factor of 4. So this becomes 3 over 7, and then put the negative sign wherever you want. Um, So then this is the answer. So this was relatively straightforward compared to the other ones. We didn't have to rewrite it. We didn't have to do L'Hopital many, many times. But I did want to include it because not only are it limits to infinity, where you could encounter a 0 over 0, in fact, you could encounter it as the limit goes to 1 or any finite number as well, right? And you could also try to factor this, but I think L'Hopital also can make our life easier as long as we check that it's 0 over 0. Okay. So that is kind of all I had for L'Hopital's question, or L'Hopital type question. So I'm going to start going to a linear approximation if there are no questions on what I've covered so far.
What are the indefinite forms that um you can use? Like, it's zero over zero, infinity over infinity, regardless of the sign. Is there any others that L'Hopital applies to as well?
Yes, so what I was talking about at the very beginning, right? Everything that's check marked, so I'll make it even clearer, right? Which is check marked, right? The ones that are check marked are indeterminate forms, right? So then these are, right, if this was plus or minus infinity, and if this was plus or minus infinity, um, we would have all of those are considered the same class in indeterminate form. This again could be plus or minus infinity here. It doesn't matter. It's still the same indeterminate form. So L'Hopital's is used at combating these indeterminate forms. And like I said, there are 4 here. There's actually 7 total. We only covered 4 in this class. So I'm not going to put it in there, right? But of these 4, right? We would need to find a way to rewrite them such that it's a 0 over 0 or infinity over infinity. I think that's where we can then use L'Hopital's rule. So just because it's an indeterminate form doesn't mean we can just apply L'Hopital's rule by itself, right? We need to rewrite it so that it's a 0 over 0 or an infinity over infinity. So this I'm going to put a star by, and this I'm going to put a star by because those are the ones that you can absolutely use L'Hopital. You don't need to rewrite it. This, for example, you would need to rewrite. Um, and then something like this, you would have to rewrite, but that's maybe beyond the scope of this class. You'd have to get a common denominator. I think there was maybe one on day 15 that we talked about this, but I think if there was a problem on the exam that was a L'Hopital rule that was not a 0 over 0 or an infinity over infinity, it would most likely be a 0 times infinity situation where you have to rewrite it to get it to a 0 over 0 or an infinity over infinity and then apply L'Hopital's rule once or twice, I guess. Um, Great question. Any others?
I want to ask, so for like 1/0, you said zero is assumed to be like approaching from the right-hand side that's very close to zero. Can it also be from the left-hand side and that's like going to negative infinity? And if it's just zero itself, that's do not exist. So the only three possible answers do not exist, infinity and negative infinity, and but that's still not indeterminate.
That's not indeterminate. So in this form, we don't know if it's approaching from the left or the right. And in fact, in that case, we know that the limit doesn't exist at that point. As you mentioned, if we had 1 over x and x was exactly equal to 0, you said it perfectly. It does not exist at that point, right? And then we would have a vertical asymptote at 0, depending on which way we approach. But that doesn't, just because the limit doesn't exist there, doesn't mean it's automatically an indeterminate form. In fact, we saw many limits where the limit didn't exist at a point, but we didn't call it an indeterminate form, right? Indeterminate forms are the ones that if I came up with another sort of situation like this, they would always have that horizontal asymptote, or I'm sorry, the vertical asymptote there. So they're all the same in that way. We can't exactly figure out what's going on there.
Okay,
Does
thank
that,
you.
okay, great. Awesome. Any other questions? Okay. Hearing none, let's do a linear approximation question. And first of all, right, when we first encountered linear approximations, we didn't know other types of derivatives, right? So I'm actually giving you this function that I say I want to get a linear approximation of this function, right? But if, for example, we said, I want to determine the value of 32.5 to the cube root, I'm sorry, the fifth root, right? If we said determine this value, right? When we first introduced linear approximations on day 9 or 10, right, we only knew the derivative of x to some power p, right? But since then, we've learned, well, what if we have the base as 32.5 and the variable is um, the the variable is actually here, right? So it becomes an exponential equation. Why can't I do it this way? And I think that that's a very good observation. But the whole point of these linear approximation questions are, can we use numbers that we know to get a good approximation, right? So here, if you remember, this would require, right, if I took the derivative, it would require a natural log of 32.5. I don't know that off the top of my head. And you probably don't either, right? So that is why it's not helpful to think of it in this way, because we don't know. We could linearize around the point, but it doesn't necessarily help us because we would still need to compute ln of 32.5. So if we had a calculator to compute that, then we would just plug in this equation and figure it out, right? So the whole idea is you don't have a calculator, you want to figure it out. So that's why we're doing something like this, right? X, in our case, x to the 1/5, not 32.5 to the x. Okay. So that's what I want to do is just acknowledge that we want you to make sense and be able to do cool math without using a calculator just by doing the linearization, right? So the first thing we want to do, right, is and also whenever you see a linear approximation, oh, can't spell linear. You should think two things and they're related. The first is it's just a tangent line, right? It's just the tangent line at a point. That's all we're figuring out, right? And we know how to do tangent lines throughout this whole class. And in fact, we know how to do tangent lines specifically with the point slope form. Okay, so that's the goal. Anytime we see a linear approximation, we're going to remember it's just the tangent line and we need to use point slope form. Okay, so first, since I gave us the function f of x, right, equals x to the 1/5, then I would need to figure out f prime of x, which equals, this is just, as I mentioned, it's a power rule. So we have 1 over 5, x to the minus 4 over 5, right? And we could rewrite that as 1 over 5, x to the 4/5. Okay. Now, another thing we need to do with our linearization or our tangent line is we need to figure out at what point is it centered, right? So that's equivalent to figuring out what value is 32.5 close to that we know the fifth root of it, right? Um, so for example, it would be a equals 2 since 32, the cube root of, or the fifth root of 32 is 2, right? Or another way is 2 times 2 times 2 times 2 times 2 equals 32, which is close to 35. Okay. So I think that's really important to know. And so then this is going to be the point that we center it around, right? The point that we absolutely know in our tangent line and our point slope equation, right? And another thing we just figured out is f of 32 equals 2, right? So this is our x, or this is our y1, and this is our x1 in the equation, right? And so lastly, we need to figure out f prime at 32 because we don't care about the slope anywhere. We care about the slope at this specific point, 32, 2, right? So that means we're just plugging in 32 here. So we have 1 over 5 x to the, or 32 to the 4/5. I don't know this off the top of my head, but I do know that this is the same as 1 over 5, the fifth root of 32 to the fourth, right? And I just established that the fifth root of 32 is 2, so this equals 1 over 5 times 2 to the fourth, which equals 16, right? So that means 1 over 5 times 16. Okay. So now we need to put this all together into our tangent line equation. Ln of x equals the slope that we found, which was 1 over 5 times 16, x minus x1, which we said is 32. And then we can't forget the fact that we have to add 2 because originally it was y minus y1, right? And y1 is 2. We move it to the other side. So this is our equation. We're almost done. We do need to plug in, um, right, in our linearization, 32.5 here, which equals 1 over 5 times 16. And then this is going to be 32.5 minus 32 plus 2. Okay, so I'm now seeing that this equals 1 over 2 times 5 times 16 plus 2, which if you simplify this at 2 times 5, that's going to equal 10. So this is 2 plus 1 over 160, which equals 2.0062. I ran out of room. Okay, let me rewrite it here. Equals 2.00625. Okay. So now another thing that we're going to ask is not only can we get a good approximation to this, but we want to figure out, I would say it's a pretty good approximation, but is it slightly too high or slightly too low? And that's where we figure out if it's an over or under estimate by looking at the concavity, right? So we could take the derivative of this again, right? And in fact, that's what we will do, equals, and then that is going to be minus 4 over 25 x to the 9/5, right? And since 32 is positive, we know that this is going to be positive, multiplied by a positive number. This whole thing is going to be negative then, because we have a negative divided by a positive, which is going to be less than 0, which means it's concave down. And that means that we have an overestimate, right? Because our function is actually concave down, but we assume that the concavity was 0 and it was a straight line. So that means we're going to get um an overestimate of the actual value. And I wrote it down in my notes. If you plug in 32.5 to the original function, we see that this equals 2.006211, right? Some other stuff. But this is good enough to see that we're close, right? We're to the 10,000th spot, but we are actually overestimating the function. Okay. And there really are, if we gave you a question like this, we can really only ask you questions about x to some power, and there are two different cases, right? I don't know if I have enough room. I do. Okay. So brief aside, x to some power, if the power p is greater than 1, right? So it's like x to the 3 halves, x to the 5 halves, right? That means that the graph is going to look something like this, right? And it's going to be concave up, and it's going to be n. Our tangent line is under approximating, right? And the only other way is if we had p less than 1, which is this case, right? 1/5 is 0.2, less than 1. And the graph for this is going to look roughly like this, right? Where we saw it's concave down, which means our tangent line is an over approximation, which is exactly what we found in this question, right? And and regardless of what it is, right? As long as p is something that is less than 1, we will have this behavior. As long as p is something greater than 1, we will have this behavior. So that's just something to keep in mind. We really are limited with the kind of questions we can ask with this kind of work. Okay. Are there any questions? Okay. Seeing none, right now I'm trying to come up with something a little bit more exotic, right? Because as I said, we're kind of limited with what we can ask with the linear approximation as like the fifth root of 32.5, for example. Um, but we could do something a little more exotic like this, right? Where the graph below is x squared minus x times y plus y squared equals the quantity x squared plus y squared, all of that to the 3/2 power. And specifically, we're looking at the point minus 1, 0, which was shown below. Okay. So here, I don't know I can't plug this into my calculator, right? It's an implicit function. So even if I did have a calculator, it'd be really, really hard to figure it out. So this would be another prime example of a linear approximation that we could do, right? So first of all, I'm looking at this point. We need to figure out what I can say about dy dx, right? Remember, this is an implicit function, but y is not some different variable. It's a function of x, right? So when I say dy dx, that makes sense. What can I say about the slope at this point? Is it negative, 0, positive, or we can't say anything? Um, One thing I would say is just use your eyes and draw it, right? So we have a point. Okay. So here is the tangent line. It goes through the point I care about. It only touches that point, right? So it looks like from my perspective, it's negative, right? Because the slope is going down. As I increase x, I'm going farther down in y, right? So the slope is going to be negative. Okay. So now here's like a hidden implicit differentiation question. We need to find dy dx at this point of the curve. Okay. So it looks super scary. I promise you it's not, right? So how we start is we take the derivative of both sides, x squared plus x y, I'm sorry, minus xy, plus y squared equals d dx of x squared plus y squared to the 3/2, right? So here, because they're all different terms, it's relatively straightforward. Here we're going to have to use the product rule because this is x times y of x, right? So then what I'm going to end up with 2x minus first, which is x, derivative of y, dy dx, plus second, y, derivative of x, which is just 1, right? And then we have plus y squared. So this is going to be 2y. And then again, y is the inside function, right? We could think of this as, and I'm going to erase this, y of x squared. So we're going to have to chain rule it and do the derivative with respect to the inside function times the derivative of the inside function, which in our case is dy dx. And similarly, we're going to have to do the chain rule here. So we end up with 3/2 x squared plus y squared to the 1/2 times the derivative of the inside function. The first term is relatively straightforward, 2x. And the second term, we did that before. That equals 2y dy dx. Okay. So now that we've taken the derivative with respect to both sides, we have this dy dx that appears, right? But I'm not curious about any point. I'm specifically looking at -1, 0. So this next step, I'm going to plug in, you know, x, y equals -1, 0, and evaluate it, right? So for here, I'm seeing that this is going to be -1 times 2 minus x is -1 minus dy dx plus 0 plus 2y dy dx. Well, y is 0, so this term is going to be 0 equals 3/2 x squared. Well, that's -1 squared plus 0 squared to the 1/2 times 2 to the times -1 plus, and again, y is 0, so this whole thing is 0. Okay. So this is good because 1 dy dx remains, right? So we didn't cancel out everything, right? So now what we're going to do is we're going to just solve for dy dx, right? So I'm seeing a negative and a negative. That's going to make a positive. So I'm going to have dy dx equals, that's 0, I don't care about. This I can move over, right? So I'm going to have 2 plus, here we have 3/2 times -1 squared is going to be 1, the square root of 1, times -2. Okay, so let's simplify a little more. We have 2 plus the square root of 1 is going to be 1, and then we have 3/2 times -2, which is going to equal -3, which equals -1. 2 minus 3 equals -1, right? So this is our answer for dy dx. Okay. And does this make sense with what we have, right? So the first question was conceptual, and we said it was negative, and we get a negative answer. So this does make sense. And if we looked at it, right, what we could say is, yeah, I would say that's roughly for every, box it rises, it goes over 1, right? Which is the exact definition of rise over run. So it looks like, yeah, about -1. In fact, exactly -1. Okay. So now, which of the following is the equation to the tangent line at the curve, right? Remember, we would have L of x minus um, f of x, or I'll call it y to not get confusing, right? y1 equals mx minus x1. And we know the point, right? Minus 1, 0. So I have L of x equals, the slope we found is minus 1, and then x minus 1 minus negative 1, excuse me. Okay, add the opposite. So we end up with minus x minus 1 because we have to distribute the x to both terms. So it looks like, or I guess we didn't, right? I could leave it as this, but if we were to distribute the x, we would see that this equals minus x plus 1, just the same. Okay, so now we're not done, right? So again, just because we have found a tangent line, we need to figure out if it's an over or underestimate, and something about it. Okay, so first of all, I'm asking about minus 1.1 in the next question. I wish I had this graph on the other page, right? But minus 1.1 is roughly here, right? So there are two values. So there's this value here that's much, much closer to 0, and the value here, which is slightly greater than 1. Right? So what we're going to be talking about is we're going to be talking about this point. Again, it doesn't make sense to have a linear approximation at this point because we know nothing about the slope here, right? We would have to redo the entire process. So I want to talk about this point. Okay. So on the curve at input x equals minus 1.1, there are two values, a value which is slightly greater than 0 and a value slightly greater than 1. I just talked about them. We're going to be looking at the lower point, right? So as I mentioned, based on your answer before, we have Lx equals minus x minus 1, okay? And what we do is we just plug in our point, right? Minus 1.1 equals the opposite of minus 1.1 minus 1, right? So then we're going to simplify. This equals 1.1 minus 1, so this equals 0.1. So that is our approximation to the y value that is closer to x equals minus 1.1. Okay. So now that we have an approximation, again, we need to figure out something about if our approximation is too high or too low. If we use our intuition at looking at the graph, we could say, okay, well, if I zoom in really close, hopefully this works, right? My line is here, but the point on the curve is up here. So obviously it looks like I'm doing some sort of under approximation, right? Um my zero point 0.1 guess is probably too low. But relatively close, right? So that's good to know. But now we need to figure out the reasoning, right? So first, the approximation is an underestimate. Um, I'm sorry, I think I switched these, right? So this should be under, under, over, and over. My bad. Okay, so the approximation is an underestimate at the curve, um, because it's concave up at that point. Okay, that sounds like a good answer. The approximation is an underestimate since at the linearization, we're looking at a point that's more negative. Um, okay, let's go back and look, right? Even if we picked a point that was like maybe, minus 0.9, we would end up with our output, which is minus zero point 0.1 as opposed to positive zero point 0.1, but we still see that it's an underestimate, right? The point here of minus zero point 0.9 minus zero point 0.1 is still more negative under this point. So I don't think it matters necessarily where we go based on the point, right? We have an underestimate here and we have an underestimate here as well. But one is greater than minus 1 and one is less than minus 1. So I don't think that's the answer. Okay. So I'm going to cross that out. Our approximation is an overestimate because the curve is concave down. Well, one, we saw that the curve looks concave up. We don't have computations to do that, but it looks concave up, so I don't like that bit, as well as it's an overestimate. It is not an overestimate. In fact, it's an underestimate, as we saw. So this is wrong. And then again, as we talked about for a few reasons, it's an underestimate, so this has to go away, and the linearization is at -1. Again, this means nothing. Okay, so that means our answer is A. Okay, are there any questions about this? Okay, seeing none, this is our last section, so we've just completed linear approximation, and now we're going to go to curve sketching. Okay, so consider f of x whose graph is given below, it's on the next page, and remember this area function, right? Where we have 1 is our anchor point, this f indicates that it's a function f, and we're going to the upper bound of x, right? So basically what we're doing is the function as x increases, we're just moving that upper bound. We're just moving that upper bound of the integral around. Okay. So what can you say about this notation, 1a f of 1, which equals the integral from 1 to 1 f of t dt? Okay, is it greater than, less than, or equal to 0? Unfortunately, I am going to have to flip over so that we can see, right? So we're looking at 1a f of, in our case, 1, right? So that means the integral from 1 to 1 of f of t dt, right? Okay, so that means my anchor point is here, and my top point, right? I've moved x such that x is also 1. So really, what I would need to do is figure out what this integral is right here, what I drew in the dotted line. And if you're wondering to yourself, Mitchell, how do I do that? You're absolutely correct, right? So by the properties of definite integrals, we know that this is going to be 0, right? There cannot be any possible area under the curve because the width of it is 1 minus 1 equals 0, right? So I could get this output, but over a width of 0, right? The estimated area is 0. So I'm going to go back, right? And I'm going to say this, right? 1 AF of 1 is equal to 0. Okay, but now we have another question. What can we say about 1 AF of 0, which equals this integral from 1 to 0 f of t dt? So there are multiple ways we could think about it, but my favorite way is I don't like when the lower bound is greater than the upper bound. And in fact, in class, we said we can assume that the upper bound is always greater. And if it's not, we have to use that property of definite integrals where we switch the bounds, but we negate the area, right? So this becomes 0 to 1, f of t dt. Okay. So now we need to figure out 1 AF of 0 equals this 0 to 1 f of t dt. So since this entire function is above the x-axis, it all has positive signed area, right? So what we would be looking for is the integral here, just here, right? And it looks like this is all positive, right? The integral from 0 to 1 of this function, right? It's at least 1, 2, 3, and then maybe 4, right? So it doesn't matter exactly, right? But approximately it equals negative times something that's positive, right? Negative signed area, right? Which means, going back to our question, that this is actually less than 0. Okay? Now we'll go fully to this page now. On what intervals of x in 0 to 5 is 1 AF of x, right? Now x is not fixed. We're allowed to move x around, which remember is this integral from 1 to x, f of t dt. When is it increasing? On what interval, right? So remember, what we're essentially doing is we're trying to find the integral. I'm going to erase this. The integral from our starting point 1 to x, and we can move x around, right? But what we're trying to do is figure out when is this value increasing as I move x, from here we knew it was negative, and then is it increasing here? And then now it becomes zero. So we know negative to zero, it has to be increasing. And we can see that as we move x all the way up here, we're accumulating more area under the curve. And that is exactly because of the fact that this is all positive signed area, right? This is all positive signed area. So as I'm moving x more and more, I'm accumulating more positive area, right? So I would say that it's actually over the entire domain that this function is increasing. This 1af of x is increasing. Okay. And now, on what interval of x in 0 to 5 is this function concave up? So now it not matter is the area function increasing or decreasing? It matters, is it increasing at an increasing rate or is it increasing at a decreasing rate? Okay. So again, our interpretation is exactly the same. We want to find the area under the curve, and we are anchored at this one point, and then we can move this f of x around, right? Okay. So what I want to say is it's increasing the entire time as we just talked about, right? But here, if I added, a little sliver here, let's say, sure, that's positive area, but that's not this is some point A and this is A plus H where H is really small. It's positive, but it's not adding a whole lot, right? I would rather be adding an area here, right? We're over the ooh, we're over the same little H neighborhood, right? We're able to accumulate a lot more area, right? It kind of towers over this and it dwarfs. So that observation is exactly what we need to figure out, right? X plus H, right? This little H neighborhood. That's exactly what we need to figure out, or use to figure out when it's concave up. So is it increasing at an increasing rate? So it's increasing here, but as you notice, the slices that we're getting, that we're accumulating, are getting smaller and smaller. So I would say here it's increasing at a decreasing rate. And then here, something magical happens, right? Now the slices are getting bigger and bigger and bigger, right? As I'm increasing, I'm getting more and more in each individual slice, right? Culminating in this, right? This monster of a slice that I'm now adding, right? So now it's not only increasing, it's increasing at an increasing rate, which is exactly when the function is concave up. This area function is concave up. Okay. So now, um, we know it's not between 0 and 2 and 4 and 5, right? And we know because it's not there, right, between 0 and 2, the slices are getting smaller. We know the third option, the whole domain, is not going to help us at all, right? So that leaves B, which is from 2 to 4. And what's the cool thing that's happening between 2 to 4? The function, not the area function, f of t itself, is increasing, right? So if f of t is increasing, the area as we accumulate more of these slices is increasing at an increasing rate because this function is always positive. Okay, so now we have some really good information. So now let's sketch the graph of this function on 0 to 5, and I need to label one x-intercept with exact value. Okay. Okay. And if we gave you a question like this on the exam, we wouldn't give you graph paper. We would already give you axes, kind of like the last curve sketching question. We gave you axes, we gave you a practice one, and then we gave you kind of a final one, right? We wouldn't just give you graph paper and say figure it out. Okay, so let's do that's one, that's two, that's three, that's four, and that's five. They should be the same width. Okay. And then obviously that's zero. Okay. So we need to label one x-axis or one x-intercept exactly, right? And I already know, we've kind of already helped you with this, right? We know that when x is 1, right? When we have x equals 1, this 1 AF of 1 equaled 0, right? It's the area of a line, which makes no sense, right? Lines have length, they don't have area because they're very infinitesimally small, right? So we know if x equals 1, then we get a y or an x-intercept, and it goes through this point. Okay. Similarly, we know that it's negative beforehand, right? And it's always increasing, right? So it's always increasing. So that means we're probably going to get a local max at 5 since it's always increasing. There can be no critical points where it goes from increasing to decreasing. Okay, so this is good. Always increasing. Um, we have the x-intercept. Is it going to have a y-intercept? Right? That's when x equals 0. Yes, in fact, we already kind of calculated that. And it's going to be negative, right? So we have the y-intercept, x-intercept. Now what we haven't figured out is concavity, right? So we said it's only concave up from 2 to 4, right? And then it becomes concave down again. Okay. So from 2 to 4, it's concave up. So before, it's concave down. So it's probably going to look something like this. And then concavity shifts, right? And now it's concave up, and concavity shifts again. Oh, sorry. Right? So it's concave down. It goes through that point. It switches concavity. So as we've indicated before, we could do this little lines to say it starts lower than that and it ends higher than that, right? And it's concave up until 4. I don't know why it keeps doing that. Sorry. It's concave up until 4, and then at 4, it switches to being concave down again, right? So we would have something like this. The only thing I want to emphasize is it's always increasing, right? So it should be something closer to this, right? Where I just didn't draw that well, right? But at 2, it switches concavity. Okay. Are there any questions about this? And let's see if I have, I don't have it pulled up. I had the exact function I used to graph it and it pulled up. But yeah, it looked something like this, right? Okay. So seeing no more questions, let's go to the last curve sketching example, right? And for those who have stuck with me and went to the review session before, I did this exact same example, but I think it's a really good example, right? It kind of has it all, if you remember, and we're going to see, right? It has x-intercepts, it has y-intercepts, it has asymptotes, it has vertical asymptotes, horizontal asymptotes. And I think if you can understand everything in this question, the problem on the exam is going to go very smoothly for you. Um, and I will say that unlike the exam we had before, where we ask you kind of all of these steps, um, we're going to make it a little easier for you, right? This was a big chunk of your third exam or your second exam, I can't remember. But the final is all encompassing, right? So we want to make it easier for you. So we would probably say identify which graph is this function as opposed to walking you through all of this, right? So you have to look at graphs and say, yes, it has a vertical asymptote here and it has a horizontal asymptote here and it's undefined here. It's a jump discontinuity here, right? Those sort of things. Okay. But nonetheless, um we have this function x squared minus x minus 2 over x squared minus x minus 6, right? So what is the domain of x? So because this is a what we call a rational function, right? It has a nice function on top and a nice function on bottom. We know that the domain is all real numbers except for when the bottom equals 0, right? So we're going to have to factor this. Okay, so this is relatively straightforward to factor, right? So this is going to mean we have x minus 3 and x plus 2, right? And I can check my work really easily by seeing that minus 3 plus 2 is going to me a minus 1x, and then minus 3 times 2 is going to be minus 6, right? So I know that if x equals 3, this is going to be 0, or if x equals minus 2, this is going to be 0, and anything times 0 is going to be 0, right? So in fact, here's our answer. If all real numbers except, you know, these points, except when x equals 3 or minus 2. Okay. Find the y-intercept of f of x, right? Y-intercept is when x equals 0, right? So, and for a rational function, it doesn't matter what the bottom is as long as it's defined there, the top has to equal 0, right? Okay. So then we have to factor the top, right? X or I'm sorry. I got ahead of myself, right? When x equals 0, right? So we just plug in 0. So h of 0 is going to equal 0 minus 2 over 0 minus 6, which equals minus 2 over minus 6 equals 1/3. So I know the point 0, 1/3 is going to be on my graph. Okay. So now, right, find the x-intercept of f of x. This is what I was talking about. Sorry, I was so excited to get this done. I forgot which one was which. Okay, this is when x when h of x equals 0. So we need to find the x values such that h of x equals 0, right? So that means x squared minus x minus 2 has to equal 0. And again, we're probably going to have to factor this. You could use the quadratic formula, but why would you when you can factor this? And this becomes x minus 2, x plus 1 equals 0, right? So that means we have two more points added. We have minus, I'm sorry, 2. We have 2, 0, and minus 1, 0 added to this, right? Because we know at these points of x, the function is going to equal 0. And I just want to make sure that both 2 and minus 1 are still parts of the domain, right? Yes, all real numbers that aren't 3 and minus 2. And here I've got 2 and minus 1. So both are good and in the domain of the function. Does h of x have any discontinuities? If so, what kind and where, right? So as we talked about, we know it's not defined at 2 points, and probably the area around those 2 points of 3 and minus 2 will probably have some information, right? So what we're going to need to do is to figure out the limit as x goes to um, minus 2 of h of x, right? So now what we're going to do is we're going to write it in its factored form, x minus 2, x plus 1 over x plus 2, x minus 3. Okay. And so we're going to see as x approaches minus 2 from the left, what's going to happen, right? Okay. So then this is going to get very, very close to 0. All right, so then we have minus 2 times minus 2 plus 1 over something that is very, very close to 0. And then this is going to be 0 times, right? So 0. And because it's coming from the left, it's going to be slightly negative, right? Okay. So now we need to figure out minus 2 is going to equal minus 4 times minus 1 over something something slightly, oop, just kidding, slightly negative. right? So this is going to tell me that as we get closer and closer from the left, right, we're going to see that this 4 over a very, very small number, right? So then this is going to go, give me a second. I think I messed up somewhere. 3 and minus 2. You know what I did? I forgot to factor this in. There it is. Right? So minus 2 minus 3 is going to be minus 5, right? So this is actually going to be a small positive number since we're multiplying by minus 5, which is why it goes to infinity. Yes. Okay, there it is. So now we can sort of stop because we know it does have a discontinuity and one of them goes to infinity. So that means we only have three. We have vertical asymptote, which is where one or both of the limits, one-sided limits, approach infinity, which is this case. And we have the removable discontinuity, where both limits equal the same thing. It's just not defined at that point. That's not our case here, right? Because they're both finite. And then we have the jump, where the left and the right hand limit are well defined. They exist, but they just are different values, right? So since we have one that goes to infinity, we know that minus 2 is a vertical asymptote. Okay. And we could figure out the other side, right, where we would I'm gonna write it and then erase it, right? Just because I think it might be helpful, right? If we do the limit as x goes to minus 2 from the right of this factored form, x minus 2, x plus 1 over x minus 2, or x plus 2, x minus 3, we see that the top is still going to be minus 4 times minus 1. And the bottom now is going to be, this is still going to be minus 5, but then minus 2 from the left, or from the right, excuse me, plus 2, it's going to be a small positive number. So this means we have 4 over a small negative number, a small positive number times negative 1, or negative 5 in our case is going to be a small negative number. So this is going to go to negative infinity. Okay. So I'm going to draw positive infinity and then negative infinity as kind of a shorthand for what we're going to do. And then we need to test the other point. So I'm going to, like I said, I will post these notes, so I don't feel bad that I'm going to erase this work. Okay. So the other one we said was an issue is when x approaches 3, and then we're going to keep it in its factored form. X minus 2, x plus 1 over x plus 2, x minus 3. And again, we're going to approach from the left first, right? We would get this equals 3 minus 2, 3 plus 1 over 3 plus 2, which is 5. And then 3, so a number slightly smaller than 3 minus 3. So that's going to be a very small positive number, which I'm going to denote 0 minus, right? And then, so this is a positive times a positive over a negative, right? So this is going to go to negative infinity. So again, we know at 3, we have a vertical asymptote is vertical asymptote. Okay. And we know that as it approaches from the left, it's going to go down. And then by the same logic as this, right, if we go from the right, none of these values are different, but this is now positive. So this becomes positive infinity, right? Okay, great. What are the horizontal asymptotes? So this is essentially asking what is the limit as x goes to infinity and negative infinity. We're going to do infinity first, right? X squared minus x minus 2 over x squared minus x minus 6, right? So we could kind of have a L'Hopital situation here, um, if you wanted to. We could also do what we did at the original, where we divided by the largest power in the denominator. In this case, it would be x squared, right? We would divide everything by that and then send that limit. Um, but you probably have realized that if we have two polynomials by now, and they're of the same order, right? So x squared is going to grow at the same rate that x squared does, which is faster than x, right? And these constants become irrelevant as x gets very, very large. They become negligible. So you should see that this is going to approach 1 because they grow at the same rate, right? So we essentially have 1 x squared over 1 x squared as the leading terms, which means they're going to cancel out and it's going to be 1. And similarly, x as it approaches minus infinity of x squared minus x minus 2 over x squared minus x minus 6 is going to also equal 1 by the same logic, right? These that these are both, we could do L'Hopital, we could do the same thing, but they're growing or decaying at, well, actually they're growing because it's positive, right? This becomes really negative, these become negligible, but is positive, right? So this positive is actually bigger than this negative, and it's going to be an infinity over infinity, but they're growing at the same rate, so they equal 1. So that means H is only has one or horizontal asymptote. And even if we had an infinity, remember infinity can't be a horizontal asymptote. Okay. So what I'm going to do is make a sign chart of the first derivative. Okay. This, we're going to have to do the quotient rule. So h prime of x equals low d high minus high d low over low x squared minus x minus 6 squared. Okay. So I'm seeing some things here, and I'm going to try to simplify this using factored forms, right? So we know what this is, and we know how these decompose. So maybe there's some work here. Um, we also could just do the algebra real quick, and for the sake of time, that's probably what I'll do. So I'm going to see a lot of cancellations because they're very similar. The one that I'm not going to see canceled is uh specifically a minus x plus 4, and then we are going to write the bottom as x plus 2, excuse me, x minus 3 squared, right? Okay, so this is the um, first derivative, and if we wanted to make a sign chart for it, which I should have left myself more room for, um, yeah, so I'll do it right here. If I wanted to do a sign chart, we know there are 2 points where it doesn't exist, right? Minus 2 and 3. We've already talked about that. But another point where the first derivative equals 0 is something that we didn't talk about. X equals 1/2. If x equals 1/2, the top equals 0. So then that's another point we need to consider. 1/2. Okay. And we know that if it's below 1/2, the -8 is going to be dominating. right? Um, the negative 8 is going to be dominating, but the x is negative, right? So it is going to be positive on this side. And then on this other side, we know that it's going to be negative and negative because as x is bigger, the negative 8 term is dominating, right? Negative 8 times a positive number now is going to be a very negative number plus 4 still negative. Okay. So this tells us that we have at most one local maximum. Um minimum, excuse me. Okay. There are no local minimums as we've talked about because of the fact that um we have a function that is increasing and then decreasing, right? And anywhere that we have, right, these go to one, these kind of level out to one. Excuse my poor drawing, right? But we know that this, whatever this is going to be much, much smaller, right? This goes to negative infinity and this goes to negative infinity. So there's no local minimum. There is a local maximum, however, at 1/2, because as I was drawing, right, it goes from positive to negative, which tells us that there's a local maximum there. So x equals 1/2. The sign chart for the second derivative, again, we're going to have to do the quotient rule. It does get a little ugly. So I'm just going to draw it for you here because I want to save some time for questions, right? Okay, so the second derivative is positive, negative, and then positive. Okay, which I guess I kind of gave it away by drawing this, right? But that's okay. Um, we know between -2 and 3, it's concave down. And then we know at the others, it's concave up. Okay, so now let's combine all of this information into a graph and sketch it. Okay. Okay. So this is going to be -2. This is going to be 3, right? We know that it's not defined there. We know there are there are 2 points where f of x, or h of x in our case, equals 0. And that is going to be -1 here and 2 here. Okay, and then we know at -1/2, there's going to be a local maximum. Okay, and then last but not least, we know at 1, which I'll do here, that there is horizontal asymptotes, right? So now we just need to include the fact that we know that this goes to negative infinity, and this goes to negative infinity, which we computed when we were talking about our discontinuities, and this is going to be coming from positive infinity. And this is also going to be coming from positive infinity, right? And then we know that it's always concave up and it's increasing up until this point and then decreasing. So it probably is going to look something like this. Excuse me, that was a little wonky, right? Something like this. And then we know that that's always concave down, and we know it's decreasing for all of these values, and it has to be concave up. So it's probably going to look something like this. And then again, this isn't defined here. So we have those asymptotes. And then again, this has to have an asymptote at 1. So the graph probably looks something like this, combining all of the information we have. Okay. And that is one last thing I want to say is that took forever, right? That whole process took a really long time, and I'm glad that we did it for one exam so that you could really work through. What we would do here is we'd ask you some of these supplemental questions about like x-intercept, y-intercepts, concavity, increasing, decreasing, but we would then give you graphs and say which one matches what we have what we've observed about this function. So you don't have to do the whole curve sketching problem again, like we did on the exam. Okay. Are there any questions left over? If if there's no questions about this exactly, I'm going to stop the recording and then I'll hang around as well for those people who have questions. Okay. So seeing no questions, I'm going to stop the recording.